Welcome to the Core Stream. The BYE podcast presents Matrix. Complexity reduced to logic, structured elements.
BYE Matrix, Episode 10, The Physics of Water. Welcome back to the BYE Matrix. If you have returned for this 10th transmission, you have accepted the rigorous parameters of this deep immersion analysis. Today, we bypass the everyday familiarity of the substance sitting in your glass and interface directly with the molecular architecture of water itself, hydrogen bonding, pressure gradients, and acoustic propagation. We are not here to simply discuss water as a backdrop to daily life. We are here to comprehend the structural logic, physical forces, and biological dependencies that dictate its behavior, from a single molecule to an entire ocean. Prepare for a high-velocity download of absolute precision. The threshold has been crossed. BYE Matrix is now active. The molecule. Start with the formula everyone knows and almost nobody questions, H2O. 2 hydrogen atoms, 1 oxygen atom. Simple, on paper. But the geometry of that simple formula is where everything interesting begins. The oxygen atom is greedy. It pulls the shared electrons from both hydrogen atoms closer to itself, which leaves the oxygen side of the molecule slightly negative and the 2 hydrogen ends slightly positive. This is called polarity, and it turns each water molecule into a tiny magnet with a positive end and a negative end, bent into a shape close to 104.5 degrees rather than a straight line. Because of this polarity, water molecules attract each other. The slightly positive hydrogen of one molecule is drawn to the slightly negative oxygen of its neighbor. This attraction is called a hydrogen bond. A single hydrogen bond is weak, far weaker than the bond holding the hydrogen and oxygen together inside one molecule. But water molecules do not form just one hydrogen bond each. On average, each molecule in liquid water is linked to roughly 3 or 4 neighbors at any given instant, and these bonds break and reform billions of times per second. It is this constant, restless networking of molecules that gives water almost every one of its unusual properties. Consider what water should do if it behaved like other molecules of similar size. Hydrogen sulfide, for example, which has a similar molecular weight, is a gas at room temperature. Water, by every reasonable prediction based on molecular weight alone, should also be a gas at the temperatures we live in. Instead, it is a liquid, because the hydrogen bonds hold the molecules together far more strongly than weight alone would suggest. Life on this planet exists in the temperature range it does largely because of this one accident of chemistry. Surface tension. Now picture the surface of a still pond. A water strider walks across it as if the water were a solid sheet. A drop of dew sits on a leaf, refusing to spread flat, holding itself into a near-perfect sphere. This is surface tension, and it is a direct consequence of the hydrogen bonding just described. Inside the body of the liquid, every water molecule is surrounded on all sides by other water molecules, pulling on it equally in every direction. The forces cancel out. But at the surface, where water meets air, there are no water molecules above to pull upward. The molecules at the surface are therefore pulled sideways and downward by their neighbors below and beside them, with nothing pulling back from above. The result is a kind of skin, an elastic sheet formed by molecules clinging to each other more tightly at the boundary than anywhere else. That is why the water strider does not sink, why a needle placed carefully on water can float despite being denser than water itself, and why droplets pull themselves into spheres rather than spreading out flat. A sphere is the shape that gives the smallest possible surface area for a given volume, and the surface is precisely where the molecules are working hardest to minimize their exposed, understretched bonds. Surface tension also explains capillary action, the way water climbs up a thin glass tube or through the fibers of a paper towel against the pull of gravity. Water is attracted not only to itself but to certain other surfaces, particularly ones with an electrical charge distribution similar to its own, such as glass or plant cell walls. When the attraction between water and the surface, called adhesion, is stronger than the water's own internal cohesion, the liquid climbs. This is part of how trees move water from root to leaf, sometimes tens of meters against gravity, without a pump. Why is the surface of an ice cube wet? Here is a question that sounds almost childish until you try to answer it properly. Pick up an ice cube. Its surface is wet, slick, slippery enough to skate on. But ice is solid. Why does a solid, sitting well below its own melting point, behave as though a thin film of liquid is sitting on top of it? The answer lies in something called the quasi-liquid layer, sometimes called pre-melting. At the very outer surface of an ice crystal, the water molecules do not have neighbors above them to lock them into the rigid, hexagonal lattice that gives ice its crystalline structure. Molecules deep inside the ice are held in place from every direction by their neighbors, vibrating in place but unable to move freely. Molecules at the surface, missing that support from one side, are far less constrained. Even at temperatures several degrees below freezing, this outermost layer, often only a few molecules thick, behaves more like a liquid than a solid. It is this disordered surface film that makes ice slippery. For a long time, the leading explanation for ice being slippery involved pressure. The idea was that the weight of a skater on a thin blade would melt a thin film of ice beneath the blade through pressure alone, and that this meltwater acted as a lubricant. That explanation is now considered largely wrong, or at best a very small part of the picture, because the pressure a typical skater applies is nowhere near enough to lower the melting point sufficiently to explain how slippery ice actually is, and ice is slippery even standing still, without any blade pressing on it. The pre-melting layer, combined in some explanations with a small amount of frictional heating as an object slides across the surface, is now considered the dominant explanation. So an ice cube feels wet not because it is secretly melting from your hand's warmth alone, though that contributes too, but because its very surface, by its nature, already sits in a state partway between solid and liquid. Rain. Rain begins invisibly. Water evaporates from oceans, lakes, rivers, soil, and the leaves of plants, entering the atmosphere as vapor, a gas, invisible and mixed freely with the air. As this moist air rises, it cools, and cool air can hold less water vapor than warm air. At some point the air becomes saturated, meaning it holds as much vapor as it can at that temperature, and any further cooling forces some of the vapor to condense back into liquid. But condensation rarely happens in pure, empty air. Water vapor needs something to condense onto, a tiny particle called a condensation nucleus. These can be specks of dust, sea salt lifted from ocean spray, pollen, or particles from combustion and pollution. Around each of these specks, a droplet begins to grow. Millions of these droplets together form a cloud. A single cloud droplet is far too small and light to fall as rain. It might be 20 micrometers across, smaller than the width of a human hair, and it will drift for a long time, suspended by rising air currents and by the sheer resistance the air offers to something so small. For rain to fall, these droplets need to merge into much larger drops, typically through collision and coalescence. Turbulence inside the cloud causes droplets to bump into each other, and when they collide, they often merge into a single larger drop. This process repeats over and over, and eventually the drop becomes heavy enough, perhaps a few millimeters across, that gravity overcomes the updrafts holding it aloft, and it falls. In colder clouds, a second mechanism often dominates, called the Bergeron process, named after the meteorologist who first described it in detail. In these clouds, ice crystals and supercooled water droplets, meaning droplets still liquid despite being colder than 0 degrees Celsius, exist side by side. Ice crystals have a lower vapor pressure than liquid water at the same temperature, which means water vapor preferentially deposits onto the ice crystals rather than the liquid droplets. The ice crystals grow rapidly at the expense of the surrounding droplets, become heavy, and fall. If the air below the cloud is warm enough, these falling ice crystals melt on the way down and reach the ground as rain rather than snow. Much of the rain falling in temperate regions actually began its journey as ice, high in the cloud, and melted only in the final stretch of its fall. Water as the major constituent of living things. Living organisms are, to a startling degree, walking bags of water with some clever chemistry mixed in. The adult human body is typically around 60% water by mass, though this varies with age, sex, and body composition. Newborn infants can be closer to 75% water, while the proportion decreases somewhat with age. Blood plasma is roughly 90% water. Muscle tissue is around 75% water. Even bone, which seems so solid and dry, contains a meaningful percentage of water within its structure. The reason life depends so completely on water comes back, again, to that polarity described earlier. Water is what chemists call an excellent solvent, meaning many substances dissolve readily in it, because water molecules can surround and separate charged or polar particles, pulling them apart and keeping them in solution. Salts, sugars, amino acids, and countless other biologically essential molecules dissolve in water, which allows the chemical reactions of life, digestion, respiration at the cellular level, and the transport of nutrients and waste, to take place efficiently in a fluid medium. Without water acting as this universal medium, the complex choreography of biochemistry inside a living cell simply could not happen at the speed or scale that life requires. Water is also directly involved in many of the chemical reactions of life itself, not merely as a bystander solvent. In digestion, water molecules are used to break down larger molecules like proteins, fats, and carbohydrates into smaller ones, a process called hydrolysis, literally meaning to split apart using water. In photosynthesis, water is split by plants to release oxygen and provide the electrons needed to build sugars from carbon dioxide. Every breath of oxygen in the air you are breathing right now, ultimately, traces back through billions of years to water molecules broken apart inside a plant cell or a cyanobacterium. Water also plays a crucial thermal role. It has an unusually high specific heat capacity, meaning it takes a relatively large amount of energy to change its temperature, again because so much energy has to go into breaking hydrogen bonds before molecules can move faster and register as warmer. This is why the human body, being mostly water, can absorb heat generated by muscular activity without its internal temperature swinging wildly, and it is why sweating is such an effective cooling mechanism. Evaporation of water from the skin requires a large amount of energy, called the latent heat of vaporization, and that energy is drawn from the skin's surface, cooling it in the process. Ocean currents. The oceans are not still bodies of water. They move in vast, organized streams, some near the surface, some in the deep, cold darkness far below, and these currents shape the climate of entire continents. Surface currents are driven mainly by wind. Persistent wind patterns, such as the trade winds near the equator and the westerlies further north and south, drag the top layer of the ocean along with them through friction. But wind alone cannot explain the great circular current systems called gyres that dominate each major ocean basin. These form because of the combined effect of wind, the shape of the continents which block and redirect flowing water, and something called the Coriolis effect, caused by the rotation of the Earth itself, which deflects moving water to the right in the northern hemisphere and to the left in the southern hemisphere. The result is enormous rotating current systems, such as the North Atlantic Gyre, that circulate clockwise in the northern hemisphere and anticlockwise in the southern hemisphere. Beneath the surface, an entirely different system operates, driven not by wind but by differences in density, which depend on temperature and salinity. This is called thermohaline circulation, from the Greek roots for heat and salt, and it is sometimes nicknamed the global conveyor belt. In the North Atlantic, near Greenland and Iceland, surface water becomes extremely cold and, as sea ice forms and leaves salt behind in the surrounding water, extremely salty. Cold, salty water is dense, and this dense water sinks, sometimes plunging thousands of meters to the ocean floor. This sinking water then flows slowly southward along the bottom of the Atlantic, eventually joining a vast, slow circulation that winds through all the major ocean basins, rising back toward the surface elsewhere, particularly in parts of the Indian and Pacific Oceans, over a journey that can take 1,000 years or more to complete a full circuit. This global conveyor belt matters enormously for climate. The North Atlantic branch of this circulation, often referred to as the Atlantic Meridional Overturning Circulation, carries warm surface water northward from the tropics, which is a major reason why Western Europe enjoys a considerably milder climate than other regions at similar latitudes, such as parts of Canada. Scientific concern in recent years has focused on whether the melting of Greenland's ice sheet, adding large volumes of fresh, less dense water into the North Atlantic, could weaken or disrupt this circulation, since fresh water does not sink as readily as salty water, potentially altering climate patterns across the entire North Atlantic region. Pressure. Water pressure increases with depth, and it increases quickly. This single fact underlies both the engineering of submarines and the biology of diving, and it is worth understanding properly. At sea level, the atmosphere above you presses down with a pressure defined as 1 atmosphere. Water is far denser than air, so pressure increases far more rapidly as you descend into it than as you climb through the atmosphere. For roughly every 10 meters of depth in seawater, the pressure increases by approximately 1 additional atmosphere. At 10 meters depth, a diver experiences roughly 2 atmospheres of pressure, double the pressure at the surface. At 30 meters, roughly 4 atmospheres. At the deepest point of the ocean, in the Mariana Trench, nearly 11 kilometers down, the pressure reaches over 1,000 atmospheres, meaning every square centimeter of a surface at that depth bears a load equivalent to roughly a ton. This pressure has direct physical consequences for anything containing air. Gas is compressible, unlike water, so as a diver descends, the air spaces in their body, the lungs, the sinuses, the middle ear, are squeezed into a smaller volume by the increasing external pressure, which is why divers must equalize the pressure in their ears by consciously opening the eustachian tube, otherwise the pressure difference can cause pain or even damage to the eardrum. The bends. This brings us to decompression sickness, more commonly known as the bends, a condition that has killed and permanently injured divers since the earliest days of pressurized diving, and which gave the historical name Cassoon disease to the same condition when it struck workers inside pressurized underwater construction chambers, called cassoons, in the 1800s. The mechanism depends on a simple physical law: the amount of gas that can dissolve in a liquid increases as pressure increases. This is the same principle that keeps carbon dioxide dissolved in a sealed, pressurized bottle of a fizzy drink. As a diver breathes compressed air at depth, nitrogen, which makes up roughly 78% of ordinary air and which the body does not use metabolically the way it uses oxygen, dissolves into the diver's blood and tissues in increasing quantities the deeper and longer the dive continues. The danger arises during ascent. If a diver rises too quickly, the surrounding pressure drops faster than the dissolved nitrogen can be safely carried back to the lungs and exhaled. Just as opening a shaken bottle of fizzy drink too quickly causes the dissolved gas to form visible bubbles, a diver ascending too fast can develop bubbles of nitrogen gas forming directly inside their blood vessels and tissues. These bubbles can block blood flow, damage tissue directly, or trigger inflammatory and clotting responses within the body. Depending on where the bubbles form, symptoms range from joint pain and skin rashes to paralysis, and in severe cases, death. The remedy divers use to avoid this is to ascend slowly, often pausing at specific depths for planned periods of time called decompression stops, allowing the dissolved nitrogen to leave the body gradually and safely through normal breathing, rather than allowing it to come out of solution abruptly as bubbles. If bubbles do form and cause serious symptoms, the treatment is recompression, placing the patient in a hyperbaric chamber, raising the pressure back up to shrink the bubbles and force the gas back into solution, then reducing the pressure again far more slowly and carefully than the original, dangerously rapid ascent. Wastewater recycling. Every time a toilet is flushed or a sink is drained, that water begins a journey through an engineered system designed to remove contaminants before the water is returned, in one form or another, to the environment or, in some cases, back into the drinking supply. The process generally happens in stages. Preliminary and primary treatment involves passing the wastewater through screens to remove large solid debris, then allowing it to settle in large tanks, where heavier solid material, called sludge, sinks to the bottom and is removed, while lighter material, such as fats and oils, rises and is skimmed from the surface. Secondary treatment relies on biology rather than mechanics. The partially cleaned water is introduced to colonies of bacteria and other microorganisms, often in aeration tanks where air is bubbled through the water to supply the oxygen these microorganisms need. The bacteria consume the dissolved organic material remaining in the water as their food source, breaking it down and converting it into carbon dioxide, water, and additional bacterial cells, which can then be separated out as more sludge in a further settling stage. Tertiary treatment, where required, removes remaining nutrients such as nitrogen and phosphorus, which can cause algae overgrowth if released into rivers or lakes in large quantities, and disinfects the water, commonly using chlorine, ultraviolet light, or ozone, to destroy remaining pathogens before the treated water, now called effluent, is released. In places facing severe water scarcity, this process is pushed even further, into what is called potable reuse, sometimes informally called toilet to tap. Highly treated wastewater is put through additional advanced steps, often including microfiltration through membranes with pores measured in millionths of a meter, reverse osmosis, which forces water through an even finer membrane under pressure to remove dissolved salts and remaining organic molecules, and advanced oxidation using ultraviolet light combined with chemical oxidants to break down any remaining trace contaminants. The resulting water can, in careful engineering terms, be purer than much natural drinking water, and several cities around the world, particularly in water-stressed regions, now incorporate treated wastewater directly or indirectly back into their drinking water supply. Desalination. Desalination addresses a different problem: how to make the vast, undrinkable salt water of the oceans usable for drinking and agriculture. Two main approaches dominate modern desalination. The first is thermal desalination, essentially an industrial-scale version of distillation. Seawater is heated, often using waste heat from power generation to improve efficiency, causing pure water to evaporate while the dissolved salts remain behind. The vapor is then collected and condensed back into liquid water, now free of salt. Various refinements, such as multi-stage flash distillation, which allows water to evaporate rapidly by exposing it to progressively lower pressures in a series of chambers, are used to make this process more energy efficient, since simply boiling seawater from scratch would be extremely costly in energy terms. The second, now more dominant approach globally, is reverse osmosis. In ordinary osmosis, water naturally moves across a semipermeable membrane from a less concentrated solution toward a more concentrated one, in an attempt to equalize concentration on both sides. Reverse osmosis, as its name suggests, forces this process to run backwards. Seawater is pushed under very high pressure against a membrane whose pores are small enough to allow water molecules through but to block the larger, hydrated salt ions. The result is fresh water on one side of the membrane and an increasingly concentrated salty brine on the other. This method requires significant energy to generate the necessary pressure, but modern energy recovery systems, which capture energy from the outgoing pressurized brine and use it to help pressurize incoming seawater, have made reverse osmosis considerably more efficient than earlier designs. the concentrated leftover brine remains a significant environmental challenge, since returning it directly to the sea in large quantities near the outlet point can raise local salinity and harm marine ecosystems if not properly diluted or managed. Glacier. A glacier is, at its simplest, a river of ice, formed where snowfall over many years exceeds the amount that melts or evaporates away each summer. As snow accumulates year after year, the weight of new snow compresses the layers beneath it. Fresh snow is full of air pockets, but under sustained pressure, the snow crystals are forced closer together, air is squeezed out, and the snow gradually transforms first into a granular, partially compacted material called fin, and eventually, often after decades of continued burial and pressure, into dense, solid glacial ice. Once a large enough mass of ice has accumulated, gravity takes over, and the ice begins to flow, slowly, like an extremely thick and sluggish liquid, downhill from the area of accumulation toward lower elevations where melting, or carving into the sea in the case of coastal glacier, removes ice at roughly the same rate that new ice arrives from above, at least in a stable climate. This flow happens partly through the deformation of the ice crystals themselves under pressure, and partly through basal sliding, where meltwater at the base of the glacier, produced by pressure and friction, acts as a lubricant allowing the entire ice mass to slide over the rock beneath it. Glacier carve the landscape as they move, grinding rock beneath them into fine sediment called glacial flour, and carrying boulders and debris that scratch deep grooves into the bedrock, grooves still visible today in many regions that were covered by ice sheets during past ice ages. Today, the retreat of glacier around the world is one of the most visible and closely monitored indicators of climate change, since a glacier represents an accumulated record of decades or centuries of snowfall and temperature, and its shrinkage reflects the balance between accumulation and melting tipping steadily toward melting. Snow and black ice. Snow forms in the same clouds where rain begins, but through a route that keeps water frozen the entire way to the ground. Rather than forming as a liquid droplet, snow begins as a tiny ice crystal, nucleating around a microscopic particle in a cold, saturated cloud, and then grows through the Bergeron process described earlier, drawing in surrounding water vapor directly as ice, without passing through a liquid stage at all. As this crystal falls and continues growing, its exact shape, whether a simple hexagonal plate, a slender needle, or the elaborate branching star shape most people picture when they hear the word snowflake, depends sensitively on the exact temperature and humidity conditions the crystal experiences on its way down, which is why snowflakes show such enormous variety in structure. Black ice, in contrast, is not black at all, but rather completely transparent, which is precisely what makes it so dangerous. It forms when a thin layer of water, perhaps from melting daytime snow, light rain, or simply condensation, freezes on a surface such as a road or pavement, typically overnight as temperatures drop. Because the ice layer is thin and forms without trapped air bubbles, it remains transparent, allowing the dark surface of the road underneath, whether asphalt or tarmac, to show clearly through it. Drivers and pedestrians see what looks like an ordinary, simply wet road, dark and unremarkable, giving no visual warning that the surface beneath their tires or their shoes is, in fact, extremely slippery ice rather than water. This combination of invisibility and treachery makes black ice one of the more dangerous winter road hazards, precisely because it defeats the visual cue, a lighter, whitish color, that people instinctively rely on to identify ice. Sonar. Sonar, an acronym for sound navigation and ranging, exploits a property of water quite different from anything discussed so far, its remarkable ability to carry sound. Sound travels through water roughly 4 to 5 times faster than it travels through air, and it can carry over enormous distances underwater with comparatively little loss of energy, especially at lower frequencies, which is precisely why sonar, rather than radar or visible light, is the primary tool used to sense the underwater world, since both radio waves and light are absorbed and scattered very quickly in water and cannot travel far beneath the surface. Active sonar works by emitting a deliberate pulse of sound, often called a ping, into the water and then listening for the echo that returns after the sound wave reflects off an object, whether a submarine, a shoal of fish, a wreck, or the sea floor itself. By measuring the time delay between the emitted pulse and the returning echo, and knowing the speed of sound in water, the distance to the reflecting object can be calculated precisely. By using an array of sensors and analyzing subtle differences in the timing and character of the returning echo, the direction and even something of the shape of the object can be estimated as well. Passive sonar, used extensively by military submarines wishing to avoid detecting their own presence, involves no emitted pulse at all. Instead, sensitive underwater microphones called hydrophones simply listen for sounds already present in the water, the noise of a ship's engines and propellers, the characteristic hum of particular machinery, or the calls of marine animals. Skilled sonar operators, and increasingly automated signal processing systems, can identify and even classify specific vessels purely from the distinctive acoustic signature their machinery produces, a kind of underwater fingerprint made of sound. Anechoic tiles. Modern submarines are frequently coated in a layer of specialized rubber tiles known as anechoic tiles, from the Greek prefix meaning without and the word for echo. These tiles serve two related but distinct purposes in the sonar battle between hunter and hunted beneath the waves. The first purpose is to absorb the sound of an enemy's active sonar pulse, reducing the strength of the echo bounce back toward the searching vessel, making the submarine harder to detect and locate in the first place. The tiles typically contain small air-filled cavities or a carefully engineered internal structure designed so that incoming sound waves lose much of their energy as heat through repeated internal reflection and absorption within the rubber and air pocket structure, rather than being reflected cleanly back the way they came. The second, equally important purpose is to muffle sound generated from inside the submarine itself, such as machinery noise, before it can radiate outward into the surrounding water and be picked up by an enemy's passive sonar listening for exactly that kind of internal noise. In this sense, the tiles work in both directions, dampening sound coming in and sound going out, which is why modern submarine design invests so heavily not only in the tiles themselves but in isolating internal machinery from the hull using flexible mountings, reducing the vibration that would otherwise be transmitted directly into the water as detectable noise. Whale song and sound propagation. Whales, particularly the great baleen whales such as humpbacks and blue whales, produce some of the loudest and most far-traveling sounds in the animal kingdom, and the physics of the ocean itself is largely responsible for how far these songs can travel. Deep in the ocean, at a depth that varies by location but is often somewhere between 600 and 1200 meters, there exists a layer where the speed of sound reaches a minimum, caused by the combined effects of decreasing temperature and increasing pressure as depth increases, two factors that affect the speed of sound in opposite directions until they balance out at this particular depth. This layer is called the Deep Sound Channel, or sometimes the SOFAR channel, an acronym for sound fixing and ranging. Sound waves that enter this channel and travel at small angles relative to it become effectively trapped within it, because any sound trying to travel upward or downward out of this layer is continually bent, or refracted, back toward the depth of minimum sound speed, since sound waves naturally bend toward regions where they travel more slowly. The result is that sound entering this channel behaves almost like light traveling down a fiber optic cable, propagating with remarkably little loss of energy over enormous distances. Sounds produced within this channel, whether by natural phenomena, underwater explosions used historically for oceanographic research, or the low-frequency calls of large whales, have been recorded traveling many hundreds, and in some documented cases, thousands of kilometers. Baleen whales appear to exploit this channel directly, often diving to depths near the sound channel's core before producing their lowest frequency calls, which suggests, though remains an area of ongoing scientific study, that these whales may have evolved to use the ocean's own acoustic architecture to communicate, coordinate, or attract mates across distances that would otherwise be utterly impossible for any sound produced by a biological organism. The Bermuda Triangle myth. Few maritime legends have captured public imagination quite like the Bermuda Triangle, a loosely defined region of the western Atlantic Ocean, roughly bounded by Miami, Bermuda, and Puerto Rico, said to be responsible for the mysterious disappearance of ships and aircraft far beyond what ordinary chance would predict. The modern legend largely traces back to a 1950 magazine article and a subsequent 1964 piece that popularized the term Bermuda Triangle itself, both drawing heavily on a small number of dramatic incidents, most famously the disappearance in 1945 of a group of United States Navy training aircraft known as Flight 19, along with a rescue aircraft sent to search for them. These stories were then repeated, embellished, and compiled across many subsequent books and articles throughout the following decades, each retelling often adding details, dramatic flourishes, or outright inventions not present in the original accounts, in a process that researchers who later investigated the claims have described as one legend essentially copying and exaggerating the last. When researchers and journalists went back to original sources, including official accident investigation reports, insurance records, and contemporary newspaper archives, rather than relying on second-hand retellings, a very different picture emerged for case after case. Investigations by the United States Coast Guard and independent researchers such as Lawrence David Cush, whose 1975 book examined the claims in detail, found that many of the supposedly mysterious disappearances had mundane, well-documented explanations available at the time, including known storms, navigational errors, mechanical failures, or, in some cases, simply that a ship or aircraft had disappeared with no wreckage ever found, which happens periodically all over the world's oceans without any regional pattern implicating the Bermuda Triangle specifically. Insurance industry data, including analyses by Lloyd's of London, and later statistical studies comparing the frequency of maritime losses within the supposed triangle against other similarly busy stretches of ocean of comparable size and traffic density, have consistently found no statistically significant excess of disappearances within the region compared to what would be expected given how heavily trafficked these particular shipping and flight routes are, and given the tropical storm activity common to that part of the Atlantic. In short, more ships and planes pass through the area than through most other ocean regions. Tropical weather there can be severe and sudden, and the accumulated legend has been built primarily through selective storytelling rather than through any anomalous physical phenomenon. Vortices. A vortex, in fluid terms, is a region within a fluid where the flow rotates around an axis, and water, given its fluid nature, produces vortices readily, ranging from the small swirl that forms as a bathtub drains to vast, powerful ocean whirlpools capable of damaging small vessels. The bathtub drain vortex is the most familiar example, and it forms because water draining through a small opening must speed up as it approaches that opening, since the same volume of water has to pass through a progressively narrower space. Any slight initial rotation present in the water, however small, whether from how the tub was filled or subtle air currents in the room, becomes dramatically amplified as the water is drawn inward, in much the same way a spinning ice skater speeds up when they pull their arms in close to their body, a consequence of the physical principle called conservation of angular momentum. Contrary to a popular claim, the direction bathtub water spins is not reliably determined by which hemisphere of the Earth you happen to be in, since the Coriolis effect that does influence rotation direction on a genuinely large, undisturbed scale, such as in cyclones, is far too weak to reliably overcome the essentially random initial conditions present in something as small and quickly drained as an ordinary bathtub or sink. On a much larger and more dangerous scale, ocean whirlpools such as the Maelstrom off the coast of Norway or the Naruto whirlpools in Japan form where strong tidal currents are forced through narrow straits or around underwater obstacles, creating powerful, sustained rotating currents capable of genuinely endangering small boats. Even though the more exaggerated maritime legends describing ships being pulled down into bottomless whirlpools have generally been considerably overstated compared to the real, still genuinely hazardous, currents involved. Vortices also appear on an entirely different scale in the atmosphere above water, in the form of waterspouts, essentially tornadoes that form over warm ocean or lake water, drawing moisture, and spray upward into a visible, rotating funnel connecting the water's surface to the base of a cloud above, driven by the same fundamental physics of rotating fluid columns that governs the tiny vortex in a draining sink. That is the full picture, or as full a picture as one transmission can hold, of a substance so common that it is easy to stop noticing it entirely. A molecule bent at just the right angle to build hydrogen bonds strong enough to hold you together, to carry a whale's voice across an ocean, to trick a diver's blood into turning against itself, to freeze into a lattice whose very surface refuses to stay solid. Water asked almost nothing of the imagination and delivered nearly all of it. The transmission ends here. If you made it this far, you were never a tourist. The comment section is open on YouTube. If you have a genuine reaction, an idea, or a specific request, leave it below. Mutual respect is assumed, not requested. Keep boosting your English. Bye for now.
Ready to boost your